Hello, it's Keith here, and this is lesson 4 of my PowerPC assembly programming tutorials. We've gone through a lot of stuff. We've learned the basics of addition and subtraction, things like that. We've done the addressing modes, and we've done comparisons. And now we're going to go back to the more obscure, slightly mathematical operations. We're going to look at logical operations, and we're going to look at shifts and a few other sign operations. Personally, I find these quite enjoyable. I think logical operations and shifts are quite fun. So let's go over to our code and let's check them out. Okay, now these might be things that you're not really familiar with if you've never done assembly before, and I'm sure some of you have done assembly many times before, and some of you maybe have just come across this because you're interested in the PowerPC. But logical operations are basically bitwise operations which are done at the bit level. Now we're going to be looking at entire registers, but the operation that's performed and the kind of comparison that's being done is being done at each bit, and we just see the final result. Now you'll know these logical operations if you've ever done any kind of electronic stuff. When I was a kid, I had these little project kits with these little microchips in them, and so I actually had heard of these sort of not and or gate kind of things, and these come into play in today's example. Okay, so what are we doing? Well, as always, what we're doing is we're loading in some test values. We're loading the test value 1, 2, 3, 4, 5, 6, 7, 8 into our registers here, and what we're going to do is we're going to use a test mask, as I'm going to call it, and we're loading that into R0 here. Now the mask is what we're going to apply to the value in our register, and we're going to perform a logical operation between the mask and the value, and we're going to store the value back into the registers. So we're going to use this value here, 1, 2, 3, 4, 5, 6, 7, 8, with this mask, and we're going to see the result of various logical operations, and the first one is referred to as AND. Now you can see we've got various versions here, but we'll look at this first one here, and we're loading the result into R3. So let's take a look. So what we've done is we've taken the value 1, 2, 3, 4, 5, 6, 7, 8 here, and we've basically performed an AND operation with that and this FF0 here. I'm ignoring all those 0 nibbles there, and the result is just 6, 7. Now why is that? Well, as I say, we're performing a logical operation, an AND operation at the bit level. So what this has said is if the bit in our source value, this 1, 2, 3, 4, 5, 6, 7, 8, and the bit in our mask, as I'm calling it, this FF0 here, are 1, then the bit in the result will be 1. Otherwise they'll be 0. And so what's happened is we've kept the 6, 7 part where the bits were 1 in the original value, but in the other bits they've all been set to 0 because they weren't 1 in both the source parameter and the mask that we applied. So the ANDing operation is effectively setting bits to 0 where they are 0 in the mask parameter. Now we've got 3 different versions here. The first one is a simple AND, so it's ANDing R6 with R0 and storing the result in R3. And C is a complement. This is basically flipping the mask parameter R0 here. So you can see here that instead of 6 and 7 being retained, because those nibbles were all 1 bits in the mask, they've actually been cleared because the mask was inverted before we did the AND. So it's actually had the sort of opposite result there with AND C, and complementing the mask. Now the final one here is AND I, which means immediate, so the mask is being specified as an immediate here, and you can also see there's a dot there, and that means that the flags register is also being updated. So you can see here that mask FF there has resulted in us keeping the 5 and 6 parts. Now for clarity, I'm always using FF here as the mask here, but of course that isn't mandatory. So we can use the value 1, 2, 3, 4 here, and then you can see that our results will be quite different. You can see this one has changed quite a bit there. But as I say, while we can use any mask we want, and you can see the effect if you look at them in binary, on a 32-bit system like this, it's easiest to work in hexadecimal, and for example purposes, I'm always setting an entire nibble to all 1 bits or all 0 bits here. So that's what AND does. Now, of course, there are a lot of other ones that are equally useful. So AND, you can kind of think of as a way of clearing bits when they're 0 in the mask, or it's kind of a way of setting bits. What it basically says is if a bit is 1 in the parameter or the mask, the result will be 1. And so this effectively sets a bit where there is a 1 in the mask, or leaves it the same where there's a 0 in the mask. So let's take a look at that. So you can see here, we starting with our value 1, 2, 3, 4, 5, 6, 7, 8 and our mask FF again. And you can see here we now end up with 1, 2, 3, 4, 5, FF8. So where the bits were 1 in the mask, they have been set to 1 in the result R3 there. R4 was the complemented version, so you can see we complemented the mask, and so all of the bits effectively that were 0 before are now set to 1 in the result, and the bits that were 1 in the original value are now left the same in the result. So a bit strange there looking at it, thinking how the normal OR works, but as I say, if you think of it as complementing the mask, complementing meaning flipping the bits, it does make sense. Now we have another one called ORIS here, or immediate shifted. Now this is taking the immediate value here and it's shifting it 16 bits into the top 16 bits of the 32-bit value, which is effectively the mask here. And when we look at R5 here, you can see that the top 2 nibbles have been set to 1 here, and that's because this part has been shifted to the very top part now. Now you'll notice here we used AND-I dot here and ORIS here, and you're probably thinking, well, you know, we're using different things each time, and you're probably wondering, are these available in all cases? And the answer is, unfortunately, no, they're not. Now, what you need to do is you need to go to my website and download the cheat sheet, or if you prefer, download the official documentation. I'm not saying my cheat sheet is better. That would be a horrendous lie, but I'm hoping it's more convenient. This is my cheat sheet. The official documentation will also tell you the options available to you. But you can see here on my cheat sheet, I've got it's very small, but you can see here under each command, all of the options are actually listed, and you can see that they're very different. You can see we've got and immediate shifted, updating the flags there with the full stop, but we've only got all immediate shifted without the full stop. But say we've got a wide variety in all cases, but the options do vary depending on the command. And so if you are looking to maybe use something a bit more tricky, a bit more unusual, there's 2 options: either check the official documentation or my cheat sheet, or simply try it and see if it assembles, and if your assembler is any good, it will refuse to assemble anything that is not possible. So either of those should work fine for you. So that's how OR works. Now let's take a look at XOR. Now XOR is a common one. I've sort of seen it a lot, so you may be familiar with it, but if you're not, basically what this does is where the bit in the mask is 1, it effectively flips the bit in the parameter that it's passed. So again, we've got R0, which is our mask as I'm calling it. So this is our mask here. And you can see we've got these nibbles where all the bits are 1, these F nibbles there of all bits 1. And these will effectively flip the matching bits in the parameter in R6 and store the result in R3. So if we look at R3 here, you will see that this was 1, 2, 3, 4, 5, 6, 7, 8. And these bits in the 6, 7 part have been flipped, and this has resulted in them being converted to 9, 8. And so those have been changed, but the other nibbles with 0 bits in them have been unchanged. So that's what XOR does. It effectively flips some of the bits. And you can see this second example here. We've done XOR immediate with FF00 here. And so you can see 1, 2, 3, 4 unchanged. 5, 6 has become A9 and 7, 8 has been unchanged. So the bits matching this mask here have been flipped. And again, we've got a shifted version which will affect the top bits. So the 1, 2 have become an ED here. So we've got an ED 3, 4, 5, 6, 7, 8, which sounds like some horrifying Robocop enemy. So there we go. So that XOR is a bit flipping operation. And as I say, the bits that are 1 in our mask will be flipped. The bits that are 0 in our mask will be unchanged. A very useful command there. Now, we're going to look at some other commands here that are maybe a little bit more obscure. One of these is NAND. Now, NAND is a bit odd. NAND effectively ANDs the parameter with the mask and then complements the result, which is different from AND-C, which complements the mask and applies it to the parameter and stores the result. So here we've got the NAND, and we are NANDing R6 with R0 and storing the result in R3. Now R3, when we did an AND, was lots of zeros, 6, 7 and a 0. Now when we've done a not AND, all of those zeros have become Fs, and the 6, 7 has become a 9, 8, just like it was here when we did a not. So you can see it's it's a little bit odd, and I'm not sure what times you'd need it, but if you want to do that, then you can do this without an extra bit flipping operation there. So it could be quite handy. Now another one that is quite unusual, something I hadn't come across before, is the equivalence command. Now this is also known as XNOR. Now this is effectively performing an XOR and then complementing the result. So what we're going to do here is we're going to load R5 with the value 0FF and R0 with the value FF0 so that we can see the effect of this equivalence operation. Now we're going to equivalent those two values together and we're going to store the result in R4. Now the result in R4 is effectively all F's followed by a 0, then an F and then a 0. Now the value F here in a nibble means that the two source nibbles were equivalent, had the same value. A value of 0 is where they didn't match. That's why we've got OFO at the bottom part of this resulting value, because the first nibble was 0 in R5 and F in R0, so they didn't match, not equivalent. But in the second nibble, they did match, they were both F, and in the third nibble, they were F and 0, so they didn't match. So the matching bits will be set to 0 and the non-matching bits will be set to 1, and this has resulted in all these F's 0 F0. So this is a way of being able to check if the bits are equivalent in two registers, and that's why it's referred to as equivalence in PowerPC commands rather than XNOR, which it might be referred to in other systems. So that's what we've done there. Now there's two other commands that are worth mentioning, I think. They're sort of related. There's the NOT command, which simply flips all of the bits, equivalent to an XOR command with a mask with all the bits as 1. So here we are flipping the bits in R6 and storing them in R3. So you can see here that we have got our value 1, 2, 3, 4, 5, 6, 7, 8, and we have flipped all the bits, and you can see that results in this value here. So that is the bit flipped version of that test value. Now the other one we've got, which is related, similar, is negate. Now NOT flips the bits, but negate will convert a positive to a minus, and the reason it's similar is the calculation method of converting a positive to a negative is we flip all of the bits in a register and we add 1. So when we flip the bits, we had ED CB A987, and when we negate it, we have ED CB 988. Now if you don't understand why that is a negative number, you need to check out my tutorial on hexadecimal negative numbers. It's a little bit complex, but when we add that to a value, it's equivalent of adding the negative of the original source value. It's a little bit odd the way hexadecimal numbers work, but you can either trust me that it works, or you can not trust me and you can look into the other tutorial on my YouTube video or look somewhere else and someone will explain to you how negative hexadecimals work when you add them to other numbers and how the values are calculated correctly. So those are the logical operations we're going to look at. Now we've briefly covered signs there, but we're going to now go into some other options with regards to signs. So we've got this section now called signs and zeros. Now basically we've looked before at loading in signed numbers, and as I said at the time, you can't load in a byte as a signed number, you can only load unsigned bytes, but you can convert numbers once they're in registered and say this is a signed value, extend it and fill the entire register. And basically this fill operation, again, how signed numbers work in hexadecimal. Basically you have to fill all of the unfilled bits with the top bit of the value that you loaded to. If you loaded a byte, you fill all of the bits with the top most significant bit of that byte, which would be bit 7 in conventional numbering. I don't even know what they want to call it with IBM bits with regards to a byte, but the top bit of that byte, or if you've got a 16-bit value, the most significant bit of that 16-bit value needs to be copied into the remaining bits of the register. Now whether that's a bit 1 or bit 0, what the result will vary. So we've got two test values here. We're loading FECD here, and then we're loading 0, 1, 2, 3, 4 here. Now the top bit in this case will be a 1, so this would be a negative number if it was 16 bits. F has a top bit of 1, so that would be a 16-bit negative number. 8-bit, the value CD in hexadecimal also has a top bit of 1, so it would be a negative 8-bit number as well. These would both be a positive number, so they've been selected for that purpose. And what EXTSB does is it extends the byte as a signed number. So we're extending R3 here as a byte, we're extending R4 as a half, so a 16-bit value, and we're doing the same here with these values here. And so the first time these are effectively negative numbers, and the second time these are effectively positive numbers. Well, let's take a look at what happens. So here are our test values. You can see here. They're both 16-bit values, but we're going to treat one as a byte and one as a half. So when we extended our byte CD, the top bit was 1, so all of the unused bits, all 24 bits, were filled with 1s, and those have become nibbles marked with F here. So that has extended that negative number into a 32-bit value from the original byte. Here we had a 16-bit word, and again the top bit was 1, so all of the bits have been filled with 1s, Fs, and that is now extended that 16-bit negative value here. But in the second case, this was a positive number, and so the top bit was 0, and so all of the other bits have been filled with 0. We use the same command, the extend commands, but because the top bit was 0, they've been filled with 0s, not with Fs there. And in the case of the byte here, the 3-4 byte, again the top bit was 0, so the extra bits have been filled with 0s. And again, this is important when we are adding signed numbers. We need all of those bits to be filled to match the signs, so that when we do our hexadecimal addition and subtraction of these signed numbers, it works correctly. And so again, this is how we would extend a byte. We can actually load a half from a memory address and sign extend it automatically, but we can't with a byte. Now, one interesting command that the PowerPC has that I can't immediately think of the time I would need it, but we have a command called count leading zeros word. Now, what this does is it will look at a 32-bit value and it will count how many zeros there are at the start of that value. So we're looking at this value in R4 here, and we're going to count the number of zeros and store the result in R5. Now, I'm going to take its word for it. I have actually checked, but basically the number of zeros on the left-hand side of that value was 13 in hexadecimal there. So that has been stored in R5. Now the value in R3 was even smaller. You can see it's only 34 there, and so that has got a total number of zeros of 1A here. I'd say you would need to check this with a hexadecimal calculator. You can use the Windows calculator to see the binary, and you can literally manually count the number of 0 bits at the start. That's what I did when I was testing this command. But again, and say not something I can immediately think of a time I'm going to need, but an interesting command and one I've never seen on another system, so definitely worth mentioning now. Now the final thing we're going to look at is something that you'll definitely need, shift commands. Now shift commands involve moving the bits around within registers, and this is something you need to do quite a lot. Often when you're working with assembly, you might be reading in values from things like, say you've got a joystick, you want to look at the fire buttons, but you read in from the joystick and the bits are in the wrong order for what you want to do, especially if you're doing multi-platform coding. You need to shift those bits around into the right order. Also, sometimes you will need to send data to something. Maybe you've got 2 bits that you want to send, but the hardware needs them to be in the top of the register that you send, and they're actually in the bottom, so you need to shift them. Another important thing about bit shifting is if you shift the bits in a register to the left by 1 bit, you effectively double the number. If you shift the bits to the right by 1 bit, you effectively halve the number. And even on systems that have multiply commands, this bit shifting is a much faster way of halving and doubling numbers than to use those multiply commands. And so that's something you may want to do when you have multiply commands, but a lot of systems don't have multiply commands like the Z80, and then it's absolutely essential. Anyway though, the point is bit shifting is a very good thing to do. Now one tricky thing is that while shifting to the left will always effectively double a value, shifting to the right, if we are working with signed numbers, we have to make sure we're using the right command, because if we shift to the right and we put a bit 0 at the very top, that negative number will become a positive number and it will break the number and it will not effectively halve that signed number. So we may need special commands to work with shift right to the right. Shift to the left we can do just fine. Okay, so that's an introduction to why shifting is important. Let's actually see some shifting occur. So what we're going to do is we're basically going to use a count of 5. We're going to run each of our loops 5 times. We've got some test values here, and we're going to be shifting those test values. So we're going to shift one bit each time. That's going to be the clearest way of seeing things happen. We can shift more than that, but 1 bit is going to be the clearest, I think. And as I say, it's effectively shifting to the left. It's effectively doubling a number each bit we shift. Okay, so we're using SLW here. So we're shifting left by a word being a 32-bit value. So we're shifting R3 to the left by R5 bits, and we're storing the result in R3 here. And then here we are shifting R4 left by R5 bits, storing the result in R4, and that full stop means we're updating the flags. Okay, well let's see what happens. Well, we've got our value 1, 2, 3, 4. We shift it to the left by 1 bit and it becomes 2, 4, 6, 8, which is very obviously double the value. Now we're repeatedly shifting it, and you can notice after 4 shifts it becomes 1, 2, 3, 4, 0. There are of course 4 bits in a nibble. One letter on this screen is a nibble, and so 4-bit shift is effectively shifting us 1 letter here. So you can see here that the values are simply moving. They're not really being lost as such. They're just moving the number of bits, and depending on their bit position, their value will change. But you can see by doing these repeated shifts, we can move that value to different places in the register. And as I say, sometimes you will want to do this if you're wanting to send data to hardware, or if you're wanting to read in a 32-bit value maybe, and maybe this is graphics data you're going to draw to the screen, but you need to split out different nibbles for the individual pixels of your screen and things. Bit shifting is very handy for that kind of thing. So there we're shifting to the left. Effectively that will double a signed or unsigned number. Shifting to the right is a little bit more tricky. We can use shift right word for unsigned numbers. That will work just fine. But if we did that for a signed number, the new bits that come in on the left hand side will be 0, and that would break the sign. What we need to do for signed numbers is SRAW, shift right algebraic word. Algebraic could be called arithmetic on other systems, but PowerPC calls it algebraic. This means signed numbers. So this is the unsigned one. This is the signed one. Now I'm actually using SRAWI just for fun here. That means use an immediate shift value. So I'm shifting 1 bit, I'm shifting R4, and I'm storing the result in R4. So these commands would effectively do the same thing. I'm just using the immediate version just for a change here. Now let's see what actually happens. Now in both cases we've got this value 8765 here. Now we are going to shift this to the right as an unsigned number in R3, and so you can see this becomes 4328 here as 1 bit has been pushed in and become an 8 there. But you can see after 4 shifts it still becomes 8765, and the top nibble there is a 0 because all of the new bits that are introduced are 0 because we're effectively halving the number each time, and that would break a signed number. So what we need to do for the signed number with our SRAWI value here is the new bits that are introduced have the same value as the original top bit. If it's negative, it stays negative. If it's positive, it stays positive. And so you can see here our 8765 after 4 shifts becomes F8765F is a nibble with entirely 1 bit because the top original bit was a 1 there. So that's what that does. Now the benefit, if you will, of shifting with algebraically or for arithmetic is whatever the original sign was, it will be maintained. So now I've changed the value from 8765 to 1765. So this is now a positive number. And so when we shift now to the right algebraically, the new bit's introduced as 0. And so effectively it's had the same result as this one. But of course, if the top bit was 1 and it was to be treated as an unsigned number, this would effectively break that number. So it is still important we use the right command depending on our value is to be treated as signed or unsigned. Now, those are the kind of bit shifting and commands you see on every system, including the lowly Z80 and the 6502. But the PowerPC doesn't stop there. In fact, it goes pretty damn crazy. It's got some very impressive commands here. These I can definitely see some very good uses for, because as I say, it's quite often I want to shift bits around from a value I've read in and move them into different places and then put them into other registers. I'm trying to read in from my joystick and make it match another system for multi-platform code. The bits are in the wrong order. I need to jumble them around, pull bits out, push them in, and usually that's multiple commands, but not the PowerPC. The PowerPC has commands that do all of these jobs in one go. And the first one we're going to look at is RLWNM. Now, I'm not quite sure how this works, but this stands effectively for rotate left word and mask. So the N is and, I guess. And what does this mean? Well, what we're going to do is we're going to do the same kind of thing as our bit shifting before. We're going to shift the bits by a certain number, but then we're going to ditch all but a certain part of the result. So we're just going to say, well, forget those bits. We only want to keep a certain range of them. So what we're going to do here is we're going to use R3 as the parameter, the first parameter here. R5 is going to be the number of bits to shift. And then this 16 to 31 in IBM bits. So remember, bit 0 is the most significant bit. Bit 31 is the least significant. And that would be bit 31 in IBM bits is bit 0 in normal bits, if you will, in every other system's bit numbering. But this is basically going to take the least significant 16 bits, and it's going to keep those, and it's going to remove the rest. So that's what this command is going to do, but because of what we set here. So we're rotating R3 by R5 bits, and we're ditching all the most significant bits here. And you can see that's exactly what's happened here. So we started with 876543221. We have shifted by R5 bits, and R5 was set to just 1 here. And so again, after the shift, we've ended up with 8643. But you can see that the top bits here have all been cleared, and that is because of this command here. Now, each time we perform this rotation, we are masking again and again. So you can see this 8643 ends up being 643 because after all of these shifts, the 8 part has effectively been lost. But you can see here that we're able to shift this. And of course, we can specify any mask that we want here. So if we wanted to keep the most significant bits, we could do 0 to 15, and we can run this again. And you can see now we are keeping the top half of the register. So, and again, this is why we do have to work in IBM bit numbering order. We can't just ignore it and use our 68,000 or Z80 bit numbering that we might be more used to. Now, this is rotating left, but it is worth bearing in mind that we can actually shift by any number of bits we want. So if we shift 31 bits, that's almost the entire register. So we're effectively shifting to the right by 1 bit by shifting to the left by 31. And that's exactly what we've done here. In fact, we can even go completely crazy and shift 32 bits, which shifts the register back into its original position because the registers are 32 bits. And so we've effectively just kept the same value there. Now, this time we were using RLWNM. We can also do RLWINM, and the immediate is the number of bits to shift. So this one is rotating R4 by 1 bit into R4, and this one is keeping bits 8 to 16, which, as I say, in IBM bits, are basically these bits here, these sort of ones. They're 8 bits from the most significant bit and all the way up to the sort of halfway point of the register there. So that is masking and only keeping a certain part of the register. Very handy. But the PowerPC goes even further with this absolutely amazing command here. RLWIMI is rotate left word immediate and mask insert bits. What does that mean? Well, what it's going to do is it's going to shift R4 by the number of bits we specify, in this case 4, and then it's going to take the bits from 16 to 31 in IBM order, and it's going to insert them into the register R3, leaving the other bits in R3 unchanged. So what does that actually result in? Well, we're going to have this test value of FFEEDDCC, which we're going to rotate. We're going to insert into 876543321. So we should be able to see pretty clearly which bits have been inserted here. Well, the bits that should be inserted are in the range of 16 to 31. So that is in the bottom half of the register. So the original value was 876543321, but then after the insertion, you can see that the top half has been unchanged, but the bottom half you can see we're inserting with these bits here, DCCF, CCFF, CFFE, and EDDC here. And these are the bits from register R4 after they've been rotated by the specified amounts here. So that's why we end up with these values here. And once again, we can change these to anything we want. We could make things nice and clear, and we could change this to 0 bits. We could rotate by 0 bits, and then we can really just see what the insertion was actually done here. So there we can see much more clearly, maybe, that it's these bottom bits here have been inserted from R4 after the shift has occurred. And of course, we can specify any range that we want. We could change this to 0 to 3 here and run again. And you'll see then that the 8 here has become an F because we have changed bits 0 to 3, inserting R4 after rotating 0 bits. And as I say, this would be a great command to have on a lot of the systems because it would allow you to do things like, as I say, the example which I often have is I've read in the joystick, the up, down, left or right are in the top 4 bits, and I want them in the bottom 4 bits, and now I have to shift them and mask them and OR them in, and this can do it all in one command. Absolutely incredibly powerful command here, so very worth you considering. Of course, if it's too hard for you, you could do this with a series of ands and ors. There's nothing really wrong with that. If you're just writing simple test games for your own fun, of course, that's fine. But you say these commands are really powerful, so if you can get to grips with them, definitely worth you considering. Anyway, that's all we've got today. As I always say, go to my website, download the source codes, the build scripts, try it all out yourself, because you can see these in action, and I'm sure they're going to be a little bit confusing to you. I've tried many times to learn things just by reading them from books, and to be honest, it's not really possible, not for me at least. I read the 68,000 books for weeks before I started programming it, and you think, oh yeah, I've read all these books and I'm sure I know it all now, and then you load up the assembly and you can't do anything because you don't fully soak up the problems until you've come across them yourself, and you don't really understand things until you've tried it yourself. So I'd strongly recommend you go to the website and download the build scripts and have a go at it yourself if you're seriously looking to do this kind of stuff. And if you're just looking for a bit of curiosity, of course it doesn't matter, but if you're really going to try and program this stuff, having a go with it yourself is really essential. We've got one more lesson coming next time with a bit more final maths and a few extra commands, but we've gone through the most of it now. Anyway, hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.